Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello students, welcome again to the TV learning programs. This is teacher Pasco, and today I will be senior for chemistry students. We are going on with unit number 6, trends in the chemical properties of group 1 elements and their compounds. The third lesson we have today is the properties of alkali metals, but here we will focus on their compounds. And it is the second part, if you remember, because there is what we discussed previously. We talked about some of the compounds of these alkali metals, like the oxides and the hydroxides. Those are some of the compounds. But there is what we didn't cover, and that is the reason why we have to go on with the second part. Look at the solubility of these substances, their thermostability, and some of their reactions. So let us go on with the objectives. At the end of this lesson, you should be able to explain or describe the solubility of some of group 1 compounds. We cannot look at the solubility of all compounds, so we will look at the trends, if there are some, and the solubilities in general of some of those compounds. And you should also be able to describe the thermostability of some of group 1 compounds, thermostability. We will also explain what is thermostability or thermodecomposition. And number 3, we should be able to describe using examples. We should also be able to give some examples. The anomalous behavior of lithium, the behaviors of lithium. You should be able to explain why it is abnormal, why it shows some abnormal properties, and you should be able to explain some of those abnormal behaviors. Good. I gave you a homework. I think you worked on it. And here I have a revision exercise, but today you are not going to get time to try them because it's very simple. So we will work together and complete and balance these equations. We have sodium oxide reacting with water. Do you remember what we get? Sodium oxide reacting with water. Sodium, that is equation number 1, sodium oxide reacting with water. What do we produce? If you remember, we said we cannot predict the solubility of these oxides. Why? Because of one reason. We know they react vigorously with water, so we cannot get their solutions. Now, what do we get when they react? The oxides react with water to produce hydroxides. So here we get sodium hydroxide and hydrogen gas. So this will be in aqueous solution. This is a gas, this is liquid, and this will be solid. Our equation is not balanced. Here we have 2. Let us put 2 here, and then we get 2 oxygen atoms. We have 2 here. Here we have 2. The hydrogen atoms, here we have 2. So we can use a half. That's it. Equation number 2, lithium oxide. We have seen that the oxides, which are basic oxides, they react with acids. So what is the product when lithium oxide react with aqueous hydrochloric acid, the acid? When they react, the basic oxides react with dilute acids to produce a salt and water. So the salt we produce is lithium chloride and H2O, water. So we use 2 here, and we have 2 here. The equation is balanced, number 3. So these equations, I've given them. Why? Because I want you to remember some to have a general review of the reactions of these compounds. If you can see it very well, here we have the oxides and the hydroxides. So we are revising the chemical properties of these oxides and hydroxides. Now let us go to equation number 3. Sodium peroxide reacting with water. We know that when the peroxides react with water, we produce what will be produced. We produce sodium hydroxide, and we do not produce water, but we produce hydrogen peroxide. Let's say it is in aqueous form. And here we use 2. So we have 2, I think the equation is balanced, 4 oxygen atoms. Here we have 4. And the hydrogen atoms, we have 4 and 4. Here we have 2 sodium atoms. And on the other side, we also have 2 sodium atoms. We have also seen that these oxides, they react. Remember, they are basic, so they should be able to react with acidic oxides, the non-metal oxides. So we have potassium oxide reacting with carbon dioxide at a high temperature. Of course, what will be produced? We produce a salt. Here we have carbon, the carbon dioxide, so we produce potassium carbonate. Potassium carbonate. That's it. And when we have a hydroxide, do you remember how we call this reaction? We have a basic substance and an acidic substance. When the two react, the two solutions, the reaction is a neutralization reaction. In a neutralization reaction, we always produce a salt and water. So the answer here will be, we have potassium hydroxide reacting with nitric acid, and we produce potassium nitrate, that is the salt we produce, plus H2O. It is a neutralization reaction. We produce non-acidic substances, and we have it balanced. Yeah, we have it balanced. And sodium hydroxide reacting with iron sulfate. Remember, we said the hydroxides of group number 1, they can precipitate metal cations from their solutions. And here is the example we have. Sodium hydroxide reacting with aqueous iron sulfate. What do we produce? We produce iron hydroxide. This is a solid substance with a dirty green color. And we produce sodium sulfate, which is soluble in water. And then we balance. And the last exercise is potassium hydroxide reacting with carbon dioxide. We've seen that these hydroxides, they can react with acidic oxides. What do we produce? We produce potassium carbonate plus H2O, liquid. Here we have 2, we need 2, and we have 2 hydrogen atoms, potassium, they are balanced, 1 carbon, and the oxygen atoms, here we have 3, 4, here we have 2 and 2, that is 4. So that is the end of our revision exercise. I hope you have understood everything and you have been able to recall all the properties we discussed about, the chemical properties about the oxides and hydroxides of these alkali metals. Now let us have a look at the solubility of the hydroxides. You have used sodium hydroxide or maybe potassium hydroxide. You know that sodium hydroxide is soluble in water. It is a substance we use, and it dissolves completely in water in an exothermic process. So this shows how these substances are soluble in water. So generally, all group 1 hydroxides are soluble in water. But even though they are all soluble in water, they don't have same solubility. You remember what we call the solubility? The amount of solute which can dissolve in 100 grams of a solvent, water, at a given temperature. So they don't have same solubility. As we move down in the group from lithium hydroxide to sodium hydroxide, potassium hydroxide, and so on, we find that, experimentally, we find that the solubility increases. And we have scientific reasons behind this increase. What are those scientific reasons? That is what we are going to have explained here. As hydroxides become more soluble in water, they produce a lot of OH ions, resulting in being strong bases. This is about the basicity of these hydroxides, but let's go back before we go deep in the basicity of these substances and explain why the solubility increases as you move down the group. To explain solubility, we use two things. We use lattice energy and hydration energy. Say lattice energy and hydration energy. What is lattice energy? Lattice energy, it is the energy released when 1 mole of an ionic crystal is formed from its constituent gaseous ions. I repeat, the energy released when 1 mole of an ionic crystal, let us say we have sodium, positive in gaseous state, combining with chlorine, negative, to produce sodium chloride, which is solid. The energy which will be produced is called lattice energy. But when sodium is dissolved in water, we get what? We get aqueous sodium. So the energy involved here is called hydration energy. When the chlorine is hydrated, let me write it like this, H2O, to get Cl negative aqueous, the energy involved is hydration energy. So hydration energy is the energy which is produced when an ion or 1 mole of ions is completely surrounded by water molecules. Now, how are these two forms of energy important to explain solubility? Lattice energy can also be looked at as the energy we need to separate ions. Because you know, the key you use to close a door is the same key you need to open the same door. So the energy that is released when ions combine is the same amount of energy you need to break apart those ions. And how does this affect solubility? If that lattice energy is very high compared to hydration energy, it will not be very easy to separate the ions, and the substance will not be soluble. But fortunately, for these hydroxides, the hydration energy is greater than lattice energy. And as we move down the group, hydration energy decreases and lattice energy also decreases, but lattice energy decreases more than hydration energy. Down the group, lattice energy decreases more than hydration energy and solubility of hydroxides increases. That is the reason. So the solubility of hydroxides increases. What about the solubility of carbonates, sulfates, and nitrate? It is the same. These substances are soluble. The compounds are soluble in water, but it is not easy to find and explain the trend in the solubility of these compounds. So here, you should be very careful. We don't use the same trend as what I have shown or what I've used to explain the solubility of hydroxides, because it doesn't work here. Here it is more complicated. So it's better to consider that they are soluble in water, but don't go deep to explain why they are soluble, because it is not very easy. We have a lot of factors which govern that, and possibly they will be covered in the future if you go on with chemistry. And here, there is a note. Hydrogen carbonates are less soluble than carbonates. Hydrogen carbonates, they are less soluble than carbonates. And we go to the next slide. The next slide is talking about the polarizing power and polarizability of ions. I have decided to explain this because it is very useful when explaining the thermostability of compounds. Thermostability means how stable or how a substance resists from being decomposed when it is heated. If it resists or if it decomposes at a very high temperature, then it means it has a very high thermostability. It is stable on heat. But if it decomposes at a low temperature, then it is less stable when heated. Now, the polarizing power, we consider it for cations. And it is the ability of a cation to distort the charges of an anion or to attract electrons, the electron cloud, towards itself, the cation. Remember, a cation is positive, and it is in the proximity of an anion which has a negative cloud. So the ability of that cation which is positive to attract towards itself the negative electron cloud is what we call the polarizing power. And you can understand that if a cation is attracting back the electrons towards itself, then the ionic character of the substance will reduce, while the covalent character will increase, because there is something of sharing which is being introduced again. So we call that the polarizing power. And the ease by which an anion can be polarized, we call that polarizability. Large anions, they have big electron clouds, and they can be attracted very easily because they are not experiencing stronger attraction from the nuclei of the anion. So a large anion, if it can be easily polarized, it will contribute to the covalent character of a compound more than the ionic character. So polarizing power, when polarizing power increases, the ionic character reduces. And when polarizability decreases, let's say when polarizability increases too, let's consider when it increases, the ionic character will also reduce. And these two will contribute to how stable an ionic compound will be when heated. If these are contributing to the reduction of this ionic character, then the compound is becoming more covalent. Becoming more covalent means that it has weaker attraction forces. And with weaker attraction forces, it can be easily decomposed. I hope this is very clear. If the attractions, the forces of attractions between particles are becoming weaker, then it will be easier. It will require a small amount of energy, heat energy, to decompose the substance. So let us go on and see what happens. The larger the anion, the higher its polarizability. And the smaller the cation and the higher its charge, the higher the polarizing power. And actually we'll use this mostly when we will be in group number 2. And then here it is said, a combination of high polarizing power and high polarizability results in too low ionic character. I have explained that enough. So we can go to the next slide and see, look at the thermostability of the alkali metal compounds. I have explained what thermostability is, which shows the resistance to decomposition when a substance is heated. And it depends on the degree of the ionic character of a compound. So thermostability of nitrates, carbonates, and hydroxides. Here it is said that it increases down the group as the ionic character increases. Why is it like that? It's because as you move down the group, the cation size increases. And when the cation size, remember we said smaller cations will have high polarizing power. So larger cations have low polarizing power. When the polarizing power decreases, the substance becomes more ionic. And with stronger electrostatic forces, they resist from being decomposed. Lithium compounds have or decompose at low temperatures, but we will see this when we will be discussing the special or the abnormal behaviors of lithium. Now, here we have the exercise. I want you to try and guess which one between potassium nitrate and cesium nitrate will decompose more easily. We have said that the thermostability increases as we move down the group, so you can choose which one. Between sodium carbonate and lithium carbonate, which one will decompose more easily? And you explain. Right, and we will have the answers in the next lesson. Write an ionic equation for the decomposition of rubidium nitrate, lithium nitrate, and potassium hydroxide. And here I want you to relate the thermodecomposition to thermostability. Thermodecomposition shows how a substance can decompose easily, while thermostability shows how a substance resists from being decomposed. Now let us see the abnormal behaviors of lithium. Lithium has a very small size. And because of that small size, it has a very high polarizing power. Because of the polarizing power, which is very high, it has, for example, salts which decompose very easily. If we take the example of lithium nitrate, when you heat it, it produces lithium oxide plus nitrogen dioxide and oxygen. And this is different from what happens when we use another nitrate, like potassium nitrate, because we produce here potassium nitrite and oxygen. And the difference here is because of the small size of lithium and its high polarizing power. You see the equations: lithium nitrate This is not right. You will ignore this one. This is a mistake. But this is how lithium hydroxide decomposes. This is the decomposition of sodium nitrate. And we have more abnormal behaviors of lithium. And mainly, we can give the examples of the low thermostability of lithium substances. You know, lithium can form normal oxides only because of its small size. Lithium substances like lithium iodide, it is more covalent than ionic, so it will decompose in organic solvents. So we have more abnormal behaviors. And when you compare to other salts or other compounds of the alkali metals, you find those of lithium to be totally different. And all that, it is because of the small size and the high polarizing power of lithium. So in the other lessons to come, we will see that it is more related to group 2 elements, which have smaller sizes, than how it is related to its group 1 members. It can form complexes, and it reacts very slowly with water compared to others. So all these are the exceptions. It forms substances like lithium nitride, but other group 1 cannot form nitride. Lithium nitride is this one. And we said they are more covalent, and because of that, they can be more soluble in organic solvents. It can form hydrides very easily. It can form carbides very easily, but other group 1 elements cannot. We also have the flame tests. Flame test of group 1, when these elements are tested on the flame, they have different colors. We have seen that when we were discussing the physical properties of these elements. So you should always remember this. And here we have the uses of group 1 metals and their compounds. You know, lithium is used in lithium batteries, in the phones. We know baking powder. We know sodium chloride, which is the table salt. We have so many uses. Sodium is used in street lighting. We have so many uses. You will read them. You can do it as a research. And then the homework. Explain the following observations. Lithium iodide is more soluble in hexane than in water. Lithium carbonate is less stable compared to sodium carbonate. Explain how you can distinguish a solution of sodium carbonate and that of cesium chloride. Which one between lithium hydroxide and potassium hydroxide is a stronger base, and write a balanced equation for the thermal decomposition of lithium nitrate and potassium nitrate. And you suggest a reason. Thank you very much for being there. See you next time.